The webinar is now broadcasting to all attendees, so welcome everybody. Over to you, David.
Yes, the number of participants is creeping up. I'll give it a moment for them to join, and then I'll welcome them. Well, good evening. Good evening, everyone. I'm David James, and I'd like to welcome you to this Institution of Engineering and Technology talk. And actually, I've just realized that the notes I was going to use are hidden somewhere underneath, but that's one of the things that we'll need to resolve. Now I've lost the whole screen. But before I introduce the speaker, there's just a couple of points I'd like to make. Firstly, your Sussex network volunteers were looking at a way that we might be able to do this sort of thing. And then the IET offered us the use of their Zoom webinar account, and that's what we're trying. So this is a bit of an experiment, because there's just a chance that in the autumn, when we start up our new program of events, that we'll have to use this technique or some combination of live talks and this sort of virtual arrangement. So if you get an email asking for your feedback, then please try and give us some feedback, because we'd like to learn as much as we can from this little experiment. The other thing that I want to talk about is how we're going to try and run this. Shortly, as I said, I'll introduce the speaker and hand over to him. But at the end, we will have a question and answer session. Now, your video, your camera, and your microphones are muted. So no one can see or hear you. So if you're eating your dinner or sipping a gin and tonic, then that's fine. You'll be all right. But for question and answers, you'll also notice if you move your cursor over the Zoom window, there's some icons appear, and one of them is labeled Q&A. So at any time during the talk, you're able to type in a question. So please just type your name and then a brief question. Keep it as brief as you possibly can. Then at the end of the talk, I'll read through those questions, and we'll see if we can come up with some answers. Okay, let's get going. It's my great pleasure to introduce Professor Mike Underhill. Now, many of you, of course, will know Mike. He's chair of our events subcommittee, which means that he organizes the program of talks that go into our little program booklet. But perhaps what you didn't know was that Mike has a degree in physics from Oxford and a second degree in electronics from the University of Surrey. So after 31 years in industry, he then spent 13 years at the University of Surrey. And although officially he's retired, he's still teaching courses there. Courses on antenna and propagation, radio frequency electronics, microwaves, and radar. And Mike is also still presenting papers at international conferences, including an e-paper at a US conference in July. However, Mike is now going to introduce us to the mysteries of quantum computing. So over to you, Mike.
Right, thank you very much. Just before you hand it over, have you got numbers of how many? I think everybody would be interested to know how many have logged on.
Well, just at the moment, I seem to have lost my, oh no, I've got it back again. Yes, we have 122 people logged on just at the moment.
Okay, well, welcome to 122 people, and I shall attempt to use the technology to talk about an appreciation of quantum computing. And David mentioned the word mysteries, but I'm not sure that mysteries should be used, or it shouldn't be used for too much longer. I will try to reduce the mystery, but increase the wonder about, that's the appreciation of quantum computing. Now, David was kind enough to mention what's on the first slide, which is I have 2 degrees. Now, that's normally I wouldn't bother with that. One in physics and one in electronics at Surrey. And the reason for mentioning it is that I think quantum computing is a really excellent example of how physics and electronics, or physics and electrical engineering, or physics and engineering, if they join together, they actually make a much better result at the end of the time. So let's progress on. So quantum computing, lots of questions. I'm sure I've not asked all the possible ones, and I'm sure you might like to ask some further ones, hopefully. So, you know, what is it? How does it differ? Where can you use it? Can you use it for cracking codes? When will it be useful? That's a good question. Is it useful already? How does it work? Why do you have to cool it? And could it ever be undercooled? Okay, there are other questions, but we'll pick up those on the way as we go. First of all, a quote from Richard Feynman, and you can look it up as a wiki quote if you wish, and that is important. I think I can safely say that nobody understands quantum mechanics. Well, quantum mechanics is the basis of quantum computing. Now, the second thing he said, nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look easy. And I would agree with certainly the second one. I would hope to slightly reduce the nobody on quantum mechanics, but not today. But let's press on. So this is something, I hope it works, and if not, we have a backup on that. But quantum computing in a nutshell, the limits of human technology. This is a little video from the Australian Academy of Science, and if you want to look it up, you can make a note of the YouTube. It's from YouTube, and I hope it works. It's the first time we've tried this kind of thing. So I'll get my arrow on and set it to going. And David, will you tell me if there's a problem?
For most of our history, human technology consisted of our brains, fire, and sharp sticks. While fire and sharp sticks became power plants and nuclear weapons, the biggest upgrade has happened to our brains. Since the 1960s, the power of our brain machines has kept growing exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. Computer parts are approaching the size of an atom. To understand why this is a problem, we have to clear up some basics. A computer is made up of very simple components doing very simple things, representing data, the means of processing it, and control mechanisms. Computer chips contain modules, which contain logic gates, which contain transistors. A transistor is the simplest form of a data processor in computers, basically a switch that can either block or open the way for information coming through. This information is made up of bits, which can be set to either 0 or 1. Combinations of several bits are used to represent more complex information. Transistors are combined to create logic gates, which still do very simple stuff. For example, an AND gate sends an output of 1 if all of its inputs are 1, and an output of 0 otherwise. Combinations of logic gates finally form meaningful modules, say for adding 2 numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all basic operations are literally simpler than first-grade math, you can imagine a computer as a group of 7-year-olds answering really basic math questions. A large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 14 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable ways we're used to, and traditional computers just stop making sense. We are approaching a real physical barrier for our technological progress. To solve this problem, scientists are trying to use these unusual quantum properties to their advantage by building quantum computers. In normal computers, bits are the smallest units of information. Quantum computers use qubits, which can also be set to one of two values. A qubit can be any two-level quantum system, such as a spin in a magnetic field or a single photon. 0 and 1 are this system's possible states, like the photon's horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of those, it can be in any proportions of both states at once. This is called superposition. But as soon as you test its value, say by sending the photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it's unobserved, the qubit is in a superposition of probabilities for 0 and 1, and you can't predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a game changer. 4 classical bits can be in one of 2 to the power of 4 different configurations at a time. That's 16 possible combinations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. 20 of them can already store 1,000,000 values in parallel. A really weird and unintuitive property qubits can have is entanglement, a close connection that makes each of the qubits react to a change in the other's state instantaneously, no matter how far they are apart. This means that when measuring just one entangled qubit, you can directly deduce properties of its partners without having to look. Qubit manipulation is a mind-bender as well. A normal logic gate gets a simple set of inputs and produces one definite output. A quantum gate manipulates an input of superpositions, rotates probabilities, and produces another superposition as its output. So a quantum computer sets up some qubits, applies quantum gates to entangle them and manipulate probabilities, and finally measures the outcome, collapsing superpositions to an actual sequence of 0s and 1s. What this means is that you get the entire lot of calculations that are possible with your setup all done at the same time. Ultimately, you can only measure one of the results, and it will only probably be the one you want, so you may have to double check and try again. But by cleverly exploiting superposition and entanglement, this can be exponentially more efficient than would ever be possible on a normal computer. So while quantum computers will probably not replace our home computers, in some areas they are vastly superior. One of them is database searching. To find something in a database, a normal computer may have to test every single one of its entries. Quantum algorithms read only the square root of that time, which for large databases is a huge difference. The most famous use of quantum computers is ruining IT security. Right now, your browsing, email, and banking data is being kept secure by an encryption system in which you give everyone a public key to encode messages only you can decode. The problem is that this public key can actually be used to calculate your secret private key. Luckily, doing the necessary math on any normal computer would literally take years of trial and error. But a quantum computer with exponential speedup could do it in a breeze. Another really exciting new use is simulations. Simulations of the quantum world are very intense on resources, and even for bigger structures, such as molecules, they often lack accuracy. So why not simulate quantum physics with actual quantum physics? Quantum simulations could provide new insights on proteins that might revolutionize medicine. Right now, we don't know if quantum computers will be just a very specialized tool or a big revolution for humanity. We have no idea where the limits of technology are, and there's only one way to find out. This video is supported by the Australian Academy of Science, which promotes and supports excellence in science. Learn more about this topic and others like it at nova.org.au. It was a blast to work with them, so go check out their site. Our videos are also made possible by your support on patreon.com. If you want to support us and become part of the Gottgesagt bird for most of our history.
Okay, well, I'll cut on the advertisements a little bit at the end, but it is, you know, a very useful video. Now, here's a little summary, picking out one or two points with some comments again, to do the comparison or pick out the key messages from there. So yes, we're down to computer parts down to the size of a few single atoms. Many, but they are very simple, or simple in they have lots of very simple gates with a few transistors, and the gates can do in their arrangement pretty well anything, but not necessarily as fast as it could be possible. So in principle, they can solve any computing problem to a very large limit. But let's go on from that. Interestingly, looking it up, the transistor gate size is now, as it showed on the video, only 14 nanometers, and that's pretty small. The important point about the 14 nanometers is that quantum tunneling of electrons is an effect. So it's a quantum effect which is actually holding up Moore's law, holding up any further improvement in the performance of computers. Basically, one effect is that it now gives high leakage currents, which causes heating. It also gives unreliable gate operation. So that really does mean that in terms of the normal classical computer, Moore's law really has reached the limit. So that's where the message comes. Why not exploit these quantum effects which have stopped Moore's law for the classical computing and move on to quantum computing. So quantum computing in a nutshell, some further bits from that. Qubits and quantum computing. Now, this is actually a point where the video is not 100% correct. Now, originally the qubit state could only be measured externally as 0 or 1, but we'll see that that's no longer entirely true, and that's very important, actually. Now, there could be perhaps as many as 20 bits worth of internal states, all superimposed and entangled, and in a sense that means that one qubit could be worth 20 bits worth of something or other, or computing power or whatever. Now the next point is that which it did indeed say, is that information of these states disappears by wave function collapse when the qubit is measured externally. But is this necessarily so? Is it a valid limit? And perhaps information theory can give an answer. And in fact, only this afternoon, I found an experiment which was reported on the web, which we'll quickly address, which actually gives an answer. And the answer is it's not completely a valid limit. And it's very, very important to realize that it's better than that particular piece of, if you like, physics dogma actually would have. It contradicts some of the classical quantum theory concepts. Right, an array of qubits indeed with quantum gates can make up a computer. It does all calculations in parallel. Now, the important thing, okay, it does them in parallel, but the present models that we have at the moment do it over a finite, a limited, in other words, stability time. And then it delivers one result and then has to start all over again. So in fact, it's done in cycles, and I'll mention that again later when So at the moment, there is a particular problem. Now, that problem is alleviated by going to very low temperatures. So the stability time at room temperature is about 200 nanoseconds, which has been achieved. And it is about 4 seconds at 15 millikelvin. Now, that's very, very cold indeed. And the improvement of about 2,000 that is inversely proportional to temperature. So it leaves open the question, is there a better way of achieving qubit stability at room temperature? So that's a question which we'll address as we go on from now on. Now, the quoted applications, which we'll mention perhaps a little bit later, database searching is much faster, and cracking of public key cryptography in reasonable time, that's the thing that makes it difficult with ordinary computers. And also perhaps the cure to that particular thing, the counter to it, is quantum cryptography, but that's an open question, as we'll see in a moment. So there are other people, there's lots of stuff on the web, and it was a very nice talk. It's over an hour, so I haven't put it up. In fact, well, sorry, it's only 40 minutes. It says on the bottom of the slide, I've just noticed. There is another one, there's one by Jim Al-Khalili, and there's another one as well, which is over an hour. But this one, I picked out one or two things out of it which haven't been said in that little video that we had already. And it is one of these lunch and learn quantum computing sessions in Sydney, Australia. And Andrea Morello is the guy giving it. And he's from, as it says, you probably can't read it, Center for Quantum Computation and Communication Technology at the University of New South Wales. So, computational power. There are that number, which I think is 10 to the 90. He claimed it was, I haven't counted them myself, particles in the known universe. So that is as many as the numbers necessary to describe the state of 300 quantum bits. We'll see the sums on that. So that's 10 to the 90 is equal to 2 to the 300. So if the target is to simulate everything, we now get to see the nature of the problem. Now, in a way, 2 to the 300, well, let's put it 300 quantum bits is not an impossible target. So that's an important point which comes out of his talk. Now, where are we at the moment? There is another interesting thing called quantum supremacy. And it's the point at which you can say that quantum computers are better than, fundamentally better than ordinary computers. Now, 50 qubits, and that's the name for which we will use, need 2 to the power 50, that's 10 to the 15 numbers, which is 1 petabyte. 70 qubits, it goes up pretty rapidly. 2 to the 70 is 10 to the 21 numbers, which is 1 zettabyte. So, different thing, this is now 70 qubits can contain as much as all the digital data on the planet. So it's not the number of particles in the universe, it's the amount of digital data on the planet. So that's another little target, if you like. Now, a 70 qubit quantum computer that exploits all the 2 to the 70 available quantum states can perform a computation that is fundamentally impossible to do by other means. And that is what is meant by quantum supremacy. So that is one target. it's actually, we'll see there's a little discussion that maybe it should be 50 qubits, but we'll come to that in a moment. So I think I've repeated myself on that. So let's go on. Quantum supremacy. In quantum compute, oh, wait a minute, let's just go back for a moment. Yes, no, it is a repeat slide, I apologize. Quantum supremacy, here's the definition. So in quantum computing, if it's the goal of demonstrating a programmable quantum device can solve a problem that no classical computer can feasibly solve, irrespective of the usefulness of the problem, and feasibly now needs to be shaded. Feasibly, in reasonable time, people would apply to that. So we then come to what is called the quantum advantage. And the quantum advantage is a demonstration that a quantum device can solve a problem merely faster than classical computers. Now, quantum supremacy is actually quite difficult. It involves engineering a powerful quantum computer and finding a computational complexity theoretic task of finding a problem that can be solved by that computer. Now that actually is a warning. At the moment, quantum computers cannot solve all the problems that an ordinary computer can. It can only solve specific kinds of problems, some of which have been mentioned in the previous video. And then it goes on with a little bit of technical speak. Super polynomial speed up are the best known problem for the task. But anyway, just note that the guy was John Preskill originally popularized that particular term of quantum supremacy. And I have been in the name dropping for a minute. I have been in the same room as John Preskill at an American conference a couple of years ago. Now, let's have a look at some of the hardware which is required for it and mention about it. And it also mentions Google's claim that they have reached the impressive milestone known as quantum supremacy. And that is, it's been very difficult. Now, you can see a picture of it there, and you can read more about the article. And one of the things which is not shown in that picture, which we'll show in a moment, is the fact that all that lot is in a container which is, as it mentions, 14 millikelvins. So here's the little argument. There's tremendous competition at the moment. It's a very active field, and it's much more active than I believed it ever would be. And we'll see a list of all the people active shortly, but the particular paper of the claim of Google's quantum supremacy has had some intriguing little things happening to them. The original paper giving details was originally posted on a NASA server, which was then hacked, if you like, or was found to be open before being quickly removed. And it turned out that this paper, the chap who put it up was one of the reviewers. But anyway, next point, copy of the paper seen by the New Scientist contains the detail of the quantum processor, called Sycamore, which had 54 superconducting quantum bits or qubits. And the claim was in relation to that. And anyway, it goes on with a bit more hype about advent of a much anticipated computing paradigm, etc. And the it only tackled one particular problem. So the caveat which I mentioned earlier should be applied. And that problem was checking as a set of numbers has a truly random distribution. Very difficult for a traditional computer if you have a lot of numbers. Now, although one of its qubits didn't actually work, the remaining 53 were quantum entangled. So we'll come back to this question of quantum entanglement and what it means with one another. And it then generated at the end of its little cycle of operation a set of binary digits and checked their distribution was truly random. Paper calculates that the task would have taken IBM Summit. Remember, this is Google speaking, and Summit is the world's best supercomputer, and Google claimed that it would take 10,000 years. But Sycamore did it in 3 minutes and 20 seconds. So that gives you some idea of the claim. As we'll see in a moment, it was a little bit overhyped, but we'll move on. So that particular paper said where the fields, what fields the quantum chip of 54 qubits would be useful. And certainly Jim Clark at Intel Labs is saying it was very good, and also saying that bigger processors will continue to be built, and but he also saying classical computing isn't giving up the fight. And this is an important point, that the goalposts keep moving on both sides. So there is likely to be a back and forth of this, you know, between quantum computing and ordinary classical computing. In simulation, then, it is expected to really improve, and that simulation classically, but the improvements on larger quantum processors will be ahead. Now later, sorry about the missing L, later John Preskill and IBM challenged the 10,000 days and claimed for the IBM Summit and said that it was actually 2.5 days because, and this is the point, the latest IBM algorithm hadn't been taken account of by Google and John Preskill, and so at the end of this little spat, quantum computing was only about 1,000 times faster. So okay, that was still quite an achievement. Now there is a tremendous competition for supremacy, and this is from Wikipedia, and I doubt if you'll be able to read it on your computers, but let me just note, Google have 4 different offerings in quantum computing: a 7x7 lattice, a 6x12 lattice, and some others. IBM have various offering computers of 2x8, 5x4, 5x4, etc., etc. I'm not sure it's got their latest offering on there at the moment. On this is a year out of date. It gives some idea of how fast things are progressing at the moment. It really is changing almost by the month. Intel had a couple of offerings on there, and Rigetti, I don't know much about, also had 3 offerings on there. But also note right at the small print at the bottom, let's use the arrow down here at the bottom, Alibaba and Baidu in China also are reported to have something going, but needless to say, there is not much in the way of details coming out. Now, those quantum computers, let's go back for a moment, are in fact these superconducting type computings of the type which we will mainly talk about, but there is another type of quantum computing called quantum annealing, which is performs a particular problem of finding a global minimum of an objective function. And anyway, it's a specialist problem, that's the point. But nonetheless, the manufacturer D-Wave is specializing in that. But note in the qubits column, let me move over, qubits, 128 qubits, 512, 1152, 2048, 5000. So this is the progress they're making. So they're having a lot more in the way of computers from that point of view. Right, let's have a look at one particular offering. This is Intel offering, and this begins to give you some idea of the shape and size of the particular processor, codenamed Tangle Lake, if you can read it, which is up here. Tangle Lake. It's a 3-inch by 3-inch chip, and it's been passed over to the Netherlands, their partner QTech, for testing at low temperatures. So it's been made presumably in the States and then moved over to the Netherlands, who have all the low temperature gear to surround it. Over here is some more details on the right hand side, and I'll give you some more detailed slides of those as we move on. So here is the magic inside, and here's the silicon chip, the qubits, and it gives some more details of how it all goes together. Interesting point down here on the bottom right hand corner, the qubit on Tangle Lake showing the Josephson junction. Now this is a means of measuring the magnetic field of the spin of a qubit and converting it to a frequency which can be measured. So that this particular chip, and lots of them, use this thing called the Josephson junction, which to actually do the readout. Moving on, and the little bit more detail, flip chip technique on that, and then untangling the name, why it was given that particular name. But anyway, that gives you a flavor of the hardware. And I should have put that in earlier. That is actually a larger version, but it has a point which I also want to mention, and that is that there are 108 radio, whoops, sorry, let's go back. There are 108 radio frequency connectors on the Tangle Lake. So these carry microwave signals onto the chip to operate the quantum bits. They're made of gold, which is excellent, etc., for anti-corrosion signal transmission. But the important bit, this is a radio frequency, an RF electronics piece of machinery. And that is where the engineers, the RF engineers, are really contributing to the whole issue. This is the example of the physics and the engineering coming together in the as an RF thing. Right, here is the IBM Q computer, which was there offering. The important thing that these computers particularly are being offered on the cloud. So researchers anywhere in the world, and I believe the figure when I saw it was 60,000 researchers, or maybe 60,000 researchers, or had been already done. So you can, if you can learn how to program this computer, you can get on the web, and I don't know what permissions you have to get, but you can program it, offer a program, and this computer will run it and give you the answer. And I wonder how many people over the world are trying to crack the various cryptography keys with this. I'm not sure it's yet quite good enough for that. Here's Google's Sycamore, a quantum computer, some other pictures, and this actually shows the bits on the top left, shows all the, and show some of the wiring on the top right, and some more with a guide to give some idea of scale, and all this lot drops down onto and then is filled up with liquid helium, which is super cooled or down to a very low degree. Right, let's move on to the quantum bits, how to explain them, and this is where the mystery is said to happen. The interesting thing, you can get the rough idea. A quantum bit, a traditional bit, can have two states, a naught or a one. Now the quantum bit, so moving down again, let's get my arrow, has many possible states, and these many possible states can be represented by points on the surface of a sphere. If you like, it's two spin axes, one spinning around the equator, and also its direction as or polarization, if you like, is another variable. So between those two, the spin and the, you have lots of possibilities. And in fact, another way of representing it is that there are a load of orbits which are shown here, and there's orbits up in the one region, and there's orbits in the one region, but in the zero region. But these orbits can be in very different positions, can contain different amount. That is supporting the idea that when you do a measurement, depending on how much energy, if you like, or phase relationship there is in up here, you will get a 70% measurement. Sorry, I clicked the wrong thing. And this 70% measurement, but that will come out of the Josephson junction or whatever as a 1 bit or a 0 bit. So what you've got to do is to do all the computing and stuff inside there. Sorry, it's difficult to use my arrow and at the same time. Right, let's see if I can tame this. Let's get back to where we were. Oops, we're going the wrong way. Apologies. Right, let's move on. I'll try and use, if I can, a pointer which is on the screen, but hopefully it won't move things on. So another way is looking here. We can see on here there is the classical bit on the top left-hand side. The qubit we've already seen is then here, and you can see now a little bit of equations to do with that. The important point is here, that there are 1 million faces. So in other words, the qubit itself has 1 million ways of representing things, faces. Now it's arguable whether those can each be 0 or 1, or whether, but down here you can see that the actual number of faces, it corresponds to 20 bits worth, if you like. And if we feed that together with this quantum computing here, we get 12 qubits there, each one of them with 1 million faces, which is 240 bits, which is 10 to the 72 possibilities. So it's getting up to the amount of data in all the world. So that's beginning to show the interest. And that also shows the importance of somehow getting a better lot of data out of this 1,000 faces on a single qubit. Now the other thing which I have, let's move it carefully over here, is compared it against this idea, against what is called quaternary amplitude modulation, which the engineers will go about, and it's showing that successively the state of, if you like, a sort of qubit can flash around between different numbers in the same way. If you ignore the four central ones on this, then around here, if you ignore those, you can see these are roughly on the surface of a sphere, and they certainly would be. But you can see the general idea of the information varying itself inside the qubit. Now let's move on. Now, this important of how much information can you get into a single, in and out of a single qubit, is actually a claim in physics world on the 2nd of October last year that a 10 qubit register breaks new ground in quantum computing. So the pictures are quite informative because they are showing paths which, let's see if I can get this thing back to, it's showing, yes, I can't do it, but it's showing these paths in here going around in a sequence. And this is showing that the claim, what is being claimed is you can make a shift register in this way with these bits going round in sequence in this particular way. So my question, and it wasn't asked in the article, is a qubit physically many surface wave paths on the surface of a conducting sphere? And what I like about it, being a lover of electromagnetism, antennas and propagation, this electromagnetic model at least sounds plausible, and it actually maps a bit of a direction for the future for improving the basic quantum computer. Now, there's another thing. If we look at the entangled matrix, which we had, let's going back to, whoops, going the wrong way. So if we look at the entangled matrix, which we had in this picture here, all these, all coupling, and I think coupling, by the way, is a much better word than entangling, because it actually represents the physics better, but it's too late now. Entanglement is going to be the word which is used, at least whatever I might think about it. Anyway, if you look at that, if we take just 4 qubits, which we see here, 1, 2, 3, 4, and if we take those 4 qubits and we look at all the possible entanglement paths, and these, and look at them in terms of 2 senses, both paths and loops, the important point is that we get very large numbers. The justification for the large numbers is all to do with this picture, which is absolutely standard stuff, maths, A-level maths, combinations, permutations, which is standard stuff. And that, from that, and looking at the picture which we have on the left, then we can see that the number of loops connecting all qubits. So looking at the order in which they're connected, and they're both forward and backwards, then it is what is called factorial n. Factorial n is, well, let's take the example which we give later for n equals 4. It is 4 times 3 times 2 times 1. And so on. Factorial 10 is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 1. So those are the factorials. But even for this 4-bit arrangement, then we have got a large number of 24. And that goes up very, very fast indeed. If we had 50, Well, actually, it was one of the numbers on one of the earlier slides. So in between the quantum, qubits, in between them, we have a large number of possibility of paths of how data can flow between them. And as far as I can see, looking at the literature which is exposed on the web, that is a possibility which has not yet been exploited, which should be perfectly possible. So is this leading towards a new quantum mode computer, which is a novel paradigm which could easily work at low room temperature, at room temperatures rather than low temperatures? So what would these look like? It also means that maybe you can make a quantum computer out of these things called nanotubes or buckyballs or so on, and here's some examples of them. And they look strangely like the ability to produce an awful lot of more than just 50 or 70 or whatever bits, and also contain an awful lot of information. There is another interesting point, which is that the single bond length of this carbon, these carbon atoms all joined up, the bonds are showed, the atoms are not, is 154 picometers, and that has a resonant frequency of 1 picohertz, which is about if they're half wavelength, it's a half wavelength, and 1,000 terahertz in the soft X-ray region. So maybe we need to push up the frequency up into beyond the optical region into this soft X-ray region to be able to make full use of this kind of computer. Or does it? Could there well be some much lower frequency modes which we could deal with this kind of computer? Anyway, mere speculation, but just to say that there are other possibilities which may well appear on the horizon. Right, wave function collapse, or perhaps it isn't not totally. On the left-hand side, it says the double slit measurement experiment tells us that the act of measuring changed the results, and the misprint, by the way, there is not mine. So does reality even exist if no one is observing? It's the Schrodinger's cat paradigm or philosophy, the problem. So anyway, it's important to consider that, because that is the reason given for saying that if you measure something, the information that what it was is then disappears and can't be used again. But in fact, again, found on the internet, there is a quantum theory which peels away the mystery of measurement, and the reference is given here, up here, and whoops, it's giving the detail of it. And anyway, this is what happens during the long mysterious collapse. So what it is saying, that this particular experiment has shown what is happening, albeit in the past, but it describes what's happening during this collapse. So now it's subdividing the collapse into little pieces. And anyway, it's a more detailed view of quantum behavior. So with my arrow gone, more detailed view of quantum behavior. And anyway, so it is a direct challenge to one of the classical rules, Schrodinger's pessimistic view, that it's actually the guys Latko Minev at Yale actually is saying that it contradicts one of the laws of quantum physics. And it is actually very important, because it means that we can extract information from a qubit without necessarily destroying that information. Very important. And let's move on. And here's another thing about quantum entanglement. This is an experiment, and this is proving that it really does happen. In this case, instead of between qubits, it is between some photons. So it's showing that photons can be used as qubits in a sense, or to someone. So actually, the field of quantum computing is quite strong, is quite more extensive than one might think. It's important because it's actually contradicts a little thing of quantum entanglement called the Bell entanglement, and actually contradicts the Bell's theorem. So it's an important thing. I won't go into the details, but the pictures, and you could follow it up. I hope there's enough information for you to do so. Now, let's move on. Public key cryptography. This is basically one of the applications what all this quantum computing can be used for. What it means is that we have Alice wanting to send a secret message to Bob. So what she does, she has already, and everybody else has, or she has Bob's public key, and she encrypts her message with that, and it comes out in this jumbled form in the middle. And then Bob has his own private key, which is linked to that public key, which can then, and only with that private key, can it decode the message to Bob. So Bob gets the message from Alice secretly, completely secretly. Now, this is the basis of something called the RSA Rivest-Shamir-Adleman algorithm, and it's really shown quite well in what has been shown above. It's called a public key cryptography because the keys can be given to anyone, but the other key must be kept private. The algorithm, now here's the important point, the algorithm is based on the fact that finding the factors of a large composite number is difficult. When the factors are prime numbers, the problem is called prime factorization. It's also a key pair of public and private key generator. Now, quantum computing is very good at factorizing, in principle, it's very good at factorizing large composite numbers, many times faster, maybe 1,000 times faster. So anyway, it will mean, if it works, if quantum computing works properly, it means that all these lovely public and private key pairs will be no longer usable, or they will be crackable. Now, the key question is whether they will be crackable within reasonable time, within time before the information is no longer useful and can doesn't give any information. So that's another part of quantum computing. Now, the other question, we're coming towards the end, by the way. The other question is that quantum cryptography, and it's a version of what we have just seen. It's more complicated in physics and engineering than what we have already seen, but in principle it has been proven. And but it is based on a rather, well, one of its aspects, one of its advantages is based on having to this particular thing. It is said, and this is copied from the web, it's impossible to copy data encoded in a quantum state. Well, we've just heard that that is no longer true within the last few months. If one attempts to read the data, then the state will be changed. It's called the no cloning, whoops, go back. It's called the no cloning theorem. And this could be used to detect eavesdropping in quantum key distribution. Well, that's no longer true. You can't detect eavesdropping anywhere near. You can probably detect it a little bit because you might see that the signal to noise ratio of your information has actually degraded slightly. But if it's big enough and strong enough, then it won't matter. And it's now a matter of signal to noise ratio. So we're coming towards the end. And another thing which quantum computing can do is quantum simulation. And can it address the problem of simulating everything? We've heard that if you have a big enough quantum computer, it can describe all the particles in the universe. So, but in fact, there is a subset of simulation, and that is the modal modeling. And that is something which I particularly like, and it's a very much underused technique, not much published at all, but in principle, it can solve any and all equations of physics, including astronomy, electromagnetics, quantum theory, and it replaces finite element methods almost completely, being typically, and that should be 1,000 times, not 100, sorry, a misprint on this slide, and it predicts the future of any system, and importantly, up to predicted limits. So it not only predicts the future of a system, but it can predict how far that prediction can be reliable and be relied upon. And quantum computing, another misprint, is the ideal way of finding the modes of the system in the first place. So quantum simulation may be quantum computing hand in hand with modal modeling. That's my own personal opinion. So now we come to the conclusions. Quantum computing is in its infancy, but it's growing much faster than Moore's law. Arguably, this is an exponential Moore's law. Well, Moore's law is already exponential, so it's an exponential of an exponential. But it's got to end somewhere. So when will that end be, and when will saturation be reached? Next point, at present, quantum computing only solves particular kinds of problems, and will it ever be able to solve any computing problem? And next, how reliable is it? How much error correction does it need? So all sorts of internal problems. What's its ultimate signal to noise ratio? And so finally, shall we continue to appreciate quantum computing forever? So on that, thank you very much. And questions? David, shall I kill my screen share?
Well, you can leave it there.
All right, okay.
We have at the moment 4 questions. So if you're feeling up to it, Mike.
Yes, indeed, yes.
The first one is from James, who says it was stated that there are 1 million faces, or 20 bits per qubit. Is that a fact, or down to how finely distinct areas on the sphere can be measured, or have been so far?
It is not a proven fact, and it does indeed. James is absolutely correct. It does indeed depend on the ability to measure the points on the sphere, and at the moment we don't know how much we can break the quantum collapse. We don't know. It's very, very early days. I think I forget the date now, but it was only a couple of months back that this latest information, the possibility, although that particular picture which showed the 1 million faces was a much older picture. Whether it was a guess, like my guess that it will come about, I don't know. But basically, my opinion is, yes, it will come about. Whether it'll be on the qubit, my personal opinion, it'll be a combination of the qubit with its entanglement paths which actually go outside the qubit. Because if you can measure an entanglement path, for example, by RF signals, without destroying it, that is, then one has a different way of getting at the information. So the answer is yes and no, but my answer is it will definitely be yes in the future.
Okay, the second question is from Luke, and he says, what do you think is the most viable and scalable approach to quantum computing? The cryogenic silicon embedded qubit chips being developed by Rigetti, IBM, Google, and D-Wave, or the laser resonated ionic qubits held in a linear ion trap being developed by IonQ?
Well, if it operates at a higher temperature, if that is correct, then the higher temperature is a big advantage. And I think that room temperature computing is actually going to be the big discriminant. I believe that room temperature quantum computing will come about, but it's a bit like room temperature superconductivity. It isn't still quite there. It may be much higher temperature, but I think my personal view is that until we have room temperature computing, we will not be able to have a quantum computer on our own desks.
Okay, then the third question is from Alan. If quantum computer can search a database fast, how can the computer ingest the assumed classical database?
Yes, another good question. The computer, the database is in a sense a passive object, or at least it is during the time it is being searched. And so the quantum computer, what part of the question is asking whether a quantum computer could itself be created to form a database. Now, if it could, then the answer would be pretty straightforward. And I think one of the things which I didn't mention is that, well, I've mentioned very briefly, was that in fact, if for those of us who remember the dynamic RAM, what you had was a load of bits all circulating around, and after a certain length of time, they got tired, if you like. They started to fade. They started to get unreliable. So you stopped and you boosted them all up to a decent value. Now, I think that dynamic RAM technique could be used to boost the performance of a quantum computer at very little loss of speed. And it might be good enough to make the qubits which have been worked at with a operating time of 200 nanoseconds, it might be able to bring them up to the 4 seconds of the qubits, so make them last, if you like, for 4 seconds rather than the 100 nanoseconds at room temperature. So that it might be possible to bridge the gap and move things up to that point. If that well possible, then it would be possible to construct a database which is really holds much more data than any of the existing databases, and it would be possible, and this is the key point, it would be possible to search it without destroying the data. The problem at the moment is that according to the laws of physics, the laws of quantum physics, I should say, that the database being read could destroy some of the data. So that's a problem. So I think one can be gently hopeful, but there isn't the answer. I would prefer, but it hasn't yet got the performance, the laser technique to the highly cooled one, because in the end, I think it might move forward. But I believe that there are other problems with the laser one, as its scalability to a high number of qubits. But I haven't researched that. Thank you for that.
Right. Okay. Well, we had a few extra questions here. We have 4 more. If
that's fine. It's fine if people could stand it.
This is from Yazan. If a qubit can have multiple values, how would you know that the value you measure is actually the correct value output of your calculation?
Yes, that is another very good question, I must say. And in fact, that if you go right back in your memory to the video, there was a throwaway comment in the video which said, which cast some doubt on whether you should have the right answer. Apologies for a moment, the telephone's going on here, but I'll rely on my wife to answer it, which she has. Right, but basically, the question is, have you got a reliable result? 2 points. One is that actually there's a lot of research on doing error correction and what is the best form of error correction for the quantum computers. There's a lot of research, so that's one point. The second point is that it's an unanswered question. If you only get one result, you can't tell whether it's a good one or not. So the answer actually given in that video is you can repeat the result many times. And if your quantum computer is very fast, you can repeat your result. And this is what you do in current simulations, finite elements and so on and so forth. You can repeat it many times to get some idea of the confidence in the simulations. So basically, one answer doesn't give the necessary, it cannot be regarded as correct. You've got to repeat it several times, okay?
Thank you. We have a question from William. Well, just before I ask that question, on the chat, I noticed someone asked whether the slides would be available. So I'm assuming, Mike, that you'll be able to upload them to our website.
Yes, I will be able to upload them. The only question is whether the video will upload. I think the answer is the video won't upload, but you and I can discuss that possibility. Okay. But in principle, yes, it can be uploaded onto the website.
Okay, well then William asks an intriguing question. He may have been watching a recent sort of science fiction series on the TV. It says, how can a small quantum computer simulate the whole universe when this would require it to be also simulating itself?
That's a lovely question. I think that's, I watched that science fiction thing that's called Devs, I think, and which is a lovely pun for Deus, which means God. But anyway, Devs, indeed, it posed essentially, it didn't pose that question directly, but it did raise the question in one's mind. And it's the answer is, I don't think it can. It's self-referential. When you say you can simulate the whole universe, it does mean the whole universe outside the quantum computer. It will be able to simulate the quantum computer, the atoms in it, but it won't be able to simulate the information that's on the atoms. Round the, if an atom is being used as a qubit, whether it's supported by laser or not, if that particular atom is got information more than just one bit on it, I don't think that the quantum computer would be able to do it. It's a self-referential problem. So I think the other point to make is, going back to my love of modal simulation. The modal simulation is a method of simulating the things very close to oneself very accurately and very quickly. But as you go further and further away and try to simulate things further and further away, you have to aggregate them. You have to consider that, for example, the motion of a planet as in its entirety. You do not try to simulate all the atoms on there. You have a rough law or set of rules which says roughly what it's like. But the further you away, the longer you ago you're looking into the universe, then in a way, the simpler it gets, the simpler the simulation gets. So I think all that external side, yes, you will indeed be able to simulate by a quantum computer. So thank you for that, William.
Well, I noticed that there's 3 remaining questions, but 2 of them are about making the slides available. And also someone has realized that the session has actually been recorded. Now, I don't know, to be honest, whether we'll have access to that, how large it will be, and whether we'll be able to do anything with it. But I'll inquire with the IET, who are essentially hosting the session. So the final question is from Phil, and he says, the qubit shift register shown in the slides, can you give any more insight to how that operates as a shift register?
Good question. The answer is not from the information that I have got available myself so far. I only found it in the last couple of days. So I hadn't managed to find whether or not there is any further information. I think there will be, and there is in the physics paper, but I have not currently got access at it. If that was Phil, yes. If Phil has got access to the physics paper which reported it, then that will be the answer. I don't currently have access to that particular physics paper. I don't have the access to IEEE Explore for physics or physical review or whatever it was in. I can't remember. So sorry, Phil. The answer is no. And but I thought it was a wonderful example because it raises questions, and the question that it raises: what is the maximum amount of information that you could contain on a single qubit? So thank you for the question, and sorry about the incomplete answer.
Actually, Mike, if you're happy, there's one final question from Caroline.
Yes.
It says, what is the likelihood that government agencies would be secret about their own quantum computer's ability to decrypt public keys? Not sure
that's a very good one.
It's good.
I think the answer is that it's out of my remit. Sorry, Caroline, but I think there will be. Well, I put it like this. Remember that what we have said, what I've said, is mainly about the hardware. I have not really talked at all about the programs, the algorithms that have been used. I think those programs and algorithms will be, at least initially, be secret. If they, it depends on the original source. I think they will be secret if they, but if somebody from somewhere else manages to independently and without any nefarious pinching of secrets, manages to figure them out, then I think, well, that has happened time and time again over the past years. So that is another question. So I think there will be at the very least, a delay in the government information coming out. I hope that answers Caroline's question.
Well, Mike, I mean, I'm a physicist as well as an engineer, and I've always struggled somewhat with quantum mechanics, and I think I'm going to continue struggling with some of the concepts within quantum computing for a little while yet. But I think we've gleaned a lot of information and basis for us all to be able to move forward. Now, if I knew how to advise people to do the virtual clap of the hands or whatever the technique is here, then I would tell them. But unfortunately, I can't see an option on my screen to be able to do that. So, Mike, it leaves it to me to thank you on behalf of the audience for your time this evening and for your, well, mind-bending talk. So thank you very much.
Okay.
Thank you everyone for joining us this evening.
Right. Cheers.
Bye-bye.